So today I'm going to talk about the boundary-layer-induced pressure field. So first I want to acknowledge my project members, 3 of my graduate students, and also our Blue Water contact, Dr. Quack, for helping us profiling the code. So the application, so the pressure field has both the fundamental and also practical significance, to understand the pressure field. Fundamentally, so pressure is we actually directly connect with vorticity, so which is an important quantity in study turbulence. And also the pressure strength term is actually one of the terms that is very hard to model when we actually try to do turbulence modeling. So understanding the pressure field will help us also deal with the modeling of turbulence. Practically, the pressure field actually will influence, for example, the vibrational loading of a flight vehicle. And also, this is the wall pressure will influence that. And also, in terms of the free stream pressure, it will influence the background noise of a supersonic wind tunnel. So this type of noise is actually a big kind of problem for do a high-speed testing and making the model you test in a wind tunnel less comparable with the free flight condition, because in the free flight condition, it's much quieter than in a tunnel condition. So this is a picture of the typical supersonic, hypersonic wind tunnel. So this is actually an experimental image, so which shows the acoustic radiation from the turbulent boundary on the tunnel wall. You can see this kind of a density gradient or pressure gradient kind of propagating away from the tunnel wall. So this will actually get to the test section, and then we'll interact with your test model and make your measurement less comparable with flight. So understanding this phenomenon is very important to actually extrapolate the data you get in this tunnel to the free flight condition. All right, so in terms of the background of this studying the pressure field, so we have very few data for this high-speed system. Measuring anything is difficult when your Mach number or when your flow speed get higher. So theoretically, theory can only predict the intensity itself. You cannot get the spectrum of this noise. Experimentally, it's also, you can only measure spatially sparse kind of points. So you cannot get the global picture. So our simulation is trying to kind of bridge the gap between try to get the more detailed information of this pressure field. So the way is to deal with you do direct numerical simulation to both get the boundary layer, which kind of radiating, and also the free stream disturbance. And then we can understand, what's the connection between the two, get the acoustic sources, and so on. All right, so this is a typical a kind of a streamwise wall normal kind of snapshot of our simulation. Essentially, we design our simulation to both model to both simulate the near surface hydrodynamic layer or the boundary layer, and also the near acoustic field, which actually radiate away from the surface, so we can get the global picture. We try to explore the parameter space from across a wide range of Mach number, wall temperature, and also the Reynolds number. So all these parameters are kind of relevant to actually different type of supersonic, hypersonic wind tunnels across the nation. So it does have practical applications. And we try to get the statistical or structural characteristic of the pressure field, including both the surface pressure and also the free stream pressure. Okay. All right, so why we want to make use of the blue water? Because getting both the turbulence field and also the acoustic field is very expensive. For example, for this type of simulation, we want our simulation box to be large enough to actually accommodate enough eddies, which can give us statistically converged results. And also, these kind of structures or this flow are kind of a broadband kind of signal. So we have to actually run this simulation for a long time to actually connect to kind of get the information of the large scales or low frequencies. And also we want to a small mesh size to actually resolve the high frequency kind of component. So this make the simulation quite expensive. Yeah, and so this box can give you a sense of what's the size of our largest simulation. So this is actually our target in the rest of the few months of this project. We want to reach a really high Reynolds number, and these runs typically will cost like more than 1,000 nodes, run with this many nodes, and it's highly scalable runs. So we want to make use of the unique capability of Blue Waters to do this type of research. Okay, so in terms of the rest of my research, the talk, at first I'm going to talk about our method, numerical method. Hopefully will help lots of you in terms of how to deal with these large-scale data sets. And then we're going to talk a few about the scientific kind of impact, and then future research. All right, so dealing with like a supersonic flow, we have a specific kind of challenging. So the challenge is like we want to actually design our numerical scheme to actually have a high resolution to actually capture the turbulence field, okay? But in the meantime, we have to do like a shock capturing to deal with the density gradient, okay, due to like the shock wave, because in supersonic case, the flow is not smooth. So we have to actually add dissipation. So it's a conflicting requirement for your numerical scheme. So for this type of study, like a spectral method, like what we heard in previous talks, will not work. So we actually resort to like a finite difference method. So this darker region is actually the high density gradient region. So this is so-called like the shock wave, eddy shock wave region. So your numerical scheme has to deal with this to make it stable. Otherwise, it will just crashes. Okay, so that's make it difficult. So the way we deal with this is use so-called a hybrid approach. So we make use of the shock capturing scheme. We use like a weighted, essentially non-oscillatory scheme, Wino scheme, to actually deal with the shock wave. And then we use a central difference scheme to deal with the smooth region or turbulence region. And then we smartly design like the shock sensor to kind of swap between the two, so that we can at the same time get to high resolution to capture turbulence, and also deal with the shock wave to make the new simulation stable. So that's the numerical method. So this is the structure of our software. So we actually solve the four kind of compressible Navier-Stokes equation. So here we have 5 primitive variables, okay? So including like the velocity, and also including like the density and the total energy. And so we have convective term. We also have the viscous term. So this is a flow around within the boundary layer. Viscous is important. And then we have different components. And then we use the explicit Runge-Kutta scheme to actually try to advance the solver. So we have a spatial part, and we also have the temporal part. The code is actually written in Fortran 2003. And currently it's MPI only, and then our Blue Water contact, Dr. Quack, is trying to help us hybridize that to both MPI and OpenMP. And we use parallel I/O, HDL5, to deal with the I/O. All right, so this is our domain decomposition. So since we deal with boundary layer flows, so we try to divide the domain, actually along the direction where we have the small changes. So we divide the domain along the streamwise direction and the spanwise direction. And then in the wall normal direction, the domain is not divided. So it's kind of a pencil type of decomposition. And then since we are not using a spectral method, we're using like a finite difference method. So essentially, we only have this kind of small overlap region. It's called the halo region. So we have at each time step, we have to exchange the neighboring kind of processor has to exchange the information. Just use this halo region. So one thing about this is like the communication time is actually minimal compared with the simulation time, because we are not deal with the global data transfer. We only deal with the local data transfer. Okay, and in terms of the scaling, so here we first talk about the computational itself. So including like the convective term, and including like the viscous term, and also the time advancement. Okay, so you can see like the code actually scales pretty well in both like the strong scaling and also in the weak scaling. Okay, so it's pretty good. And then in terms of I/O, so we deal with two types of I/Os. One is like the so-called the restart I/O. So essentially, every few thousand iterations, we write out the whole flow field for the purpose of restarting. If one round finishes, we have to restart. Just in the most recent one. So this actually includes like all the primitive variables and all the information that is required to restart a run. So this can get as large as 1 terabyte. So this is a huge data set. And in a typical run, we try to keep like about 50 such volumes. Okay, and then we also have analysis I/O. So essentially, we actually doing some kind of running average to get the flow field so that we can actually monitor our simulation, and also data intensive time series. So this time series is for us to get the spectrum, or to get this wave number, or whatever, like this quantities of interest for like at the post-processing stage. So this can get to like also 200 gigabytes per file, per dump. So also this red kind of color indicate like the large kind of files we output during a typical simulation. And then we archive a subset of that, essentially. It's like about like 50 terabytes data. Okay, so we try to give you a sense of how we deal with I/O. So as I said, we have two types of large data sets. One is a restart data sets. One is this time series data sets. So we find we actually can deal with output in so-called a one-file mode and also a multi-file mode. So in one-file mode, it's like all the processors collectively write to a single file, okay? And you can get just a large volume. But we find like this, the performance deteriorate, once the file size gets to larger than 100 gigabytes. So then after that, we actually swap to the multi-file mode. So essentially what we do is like we output like the number of files it dumps to, let it equal to like the number of X node or number of Y node. Okay, so this is kind of a balance between a single file and also the number of files that equal to the MPI ranks, because that will be too many files. So essentially it's somewhere in between. So in this way we can actually kind of post-process in a convenient way, but still we get a small number of files to maintain. Okay, so that's our strategy, and this actually pays very well. So for example, for like a 160 gigabytes dump, so if we want to use like a single file mode, you can see like the performance kind of deteriorate. You write a single file can take like nearly 30 minutes. Okay, and then once we swap to the multi-file mode. So here we output in this way, so like this, okay? And it's 0.1 minutes. Actually, this time is similar to like we make the file number equal to the MPI ranks. Okay, so this is a good balance. So we are happy about this, what we have so far. Okay, and this is the overall performance, so including both like the computing time and also the I/O time, and it scales pretty well. And since we only have an MPI code, so we make use of 32 cores per node. So since like communication time is minimum, so we still get a very good performance, a very good scaling. Okay. And this is a breakup of one of the simulations. So you can see like 85% of the time is actually spent on computing. So this 10%, I believe it should be smaller, because this probably we output more aggressively than we need to. So in a typical like production run, if we minimize our output, we can get to like less than 5%. So it's a good trade-off. Okay. All right. So before I finish the talk, I want to give you some sense of what kind of domain science, what is the interesting physics we get out of this simulation. Okay, so the purpose, we actually have developed this direct numerical simulation database of this acoustic radiation across a wide range of flow Mach numbers and also the wall temperature conditions. So these conditions actually are representative of the hypersonic wind, supersonic wind tunnels across the nation. So in the last year, we actually achieved the first successful comparison of the wall pressure spectrum against real experiments. The experiments actually are collected on the tunnel wall of a few high-speed tunnels across the country, including like the Purdue tunnel, including the Sandia tunnel, and also one of the highest Mach number tunnel in the Air Force. So we actually get a pretty decent comparison in terms of the wall pressure. So this is actually the first comparison of this wall pressure spectrum at a hypersonic speed. So the Mach number larger than 5. Okay. All right. So so this is actually a typical experiment can give you just a single point measurement. You can actually record a time history. You can get the spectrum, but you cannot get more than that. So in terms of numerics, we can actually get this spatial structure. For example, how the pressure structure changes as you move away from the wall. So this is the figure, the 3D correlation just at the wall. So the reference plane is right at the surface. You can see that the structure is pretty kind of nearly perpendicular to the surface. And then as you move away from the wall, the structure is tilted. It's actually leaning downward of the flow. So this is what's happening in the free stream. So this is the typical kind of phenomenon of eddy Mach wave radiation. So you have a preferred direction of these structures. Okay. And this is a movie we get for one of the simulations. So you can see that the acoustic field. So this gray region is actually a density gradient, which we use to visualize the free stream noise out of the boundary layer. And you can see that it has preferred direction. And also it has finite spatial scales, and it's pretty stochastic. Okay. And we can explore more physics. For example, we can study how the direction of the predominant direction of the noise depend on the free stream Mach number. So you can see that as you increase the flow Mach number from Mach 2.5 to Mach 14, the wave actually becomes shallower. So this angle is very important when we design our wind tunnel, because it will depend on how the wave actually impinging on the test section, and then will influence the so-called the quiet zone and also the noisy zones like that. So this angle is very important, okay, for this wind tunnel testing. And we can also look into the propagation of the acoustic noise. So this is actually the propagation speed of the free stream pressure fluctuation as a function of free stream Mach number. So our data is this kind of a solid symbol. Actually, is consistent with the classic experiment by Laufer in the JPL, NASA JPL tunnel, in the 60s. This is a really classic kind of experiment. And also, it's also consistent with the eddy Mach wave radiation theory, so that the eddy has to propagate supersonically with respect to the free stream for it to radiate. So essentially, our kind of data actually lies within this supersonic relative Mach number regime. Okay. And lastly, we can also investigate the noise of the acoustic fluctuation. We find that the noise is actually primarily concentrated near the surface, and is very sensitive to wall temperature of of the tunnel. So that's the major finding. So for the supersonic kind of pressure, does not satisfy the Poisson equation. So this wave equation is actually what governs this type of pressure, okay, field in a compressible fluid. All right, so I want to summarize. So we have make use of the unique capability of blue water to develop this DLS database that across a wide range of Mach numbers and wall temperature, and also a range of Reynolds number. So the Reynolds number 2000 is actually it's actually one of the largest tunnels. This is the number that is of relevant to that type of application. Okay. And this DLS field can give us the global structure of the pressure field, including the correlations, like the spectrum, the propagation speed, a lot of things were of interest to wind tunnel testing. And also, we make use of the computer, Blue Water computer, to kind of have done a lot of software kind of engineering, including like the parallel I/O and hybridize MPI with OpenMP. So those, this is some of the ongoing work. So I want to give you two sides. So this is actually ongoing work with Dr. Quack as the point of contact at Blue Waters. So we're trying to hybridize, okay, of MPI with OpenMP, essentially in the direction that is not divided. We try to make use of the thread. Okay, so that's what we are working on right now. And then lastly, since like we have done like a domain decomposition when we kind of write out our data, so we try to, to change as later as possible our post-processing code. So essentially, we want to make use of so-called these virtual data sets of the HDF5 library, so that this divided image or divided data can behave the same as you had a single kind of snapshot, so that if this could be used, then it will significantly reduce the amount of work for like post-processing the data, because a large kind of dump is kind of distributed into like multiple files. So we want to make use of this to kind of piece them together. Okay, so that's another ongoing work we are dealing with. Okay, so this finally I want to acknowledge our another collaborators, Dr. Lian at NASA London, who actually collaborated with us for quite a few years, and then Dr. Quack at Blue Waters to help us with the software profiling, and also like hybridize OpenMP with MPI, and the Air Force for providing the funding, and also PRAD for us to give us NSF, to give us the computing time. Okay, thank you very much for your attention.